Today's topic is about a graph. A graph consists of different vertices and edges. We can say that G is a graph that is composed of different vertices and edges. Vertices are connected using edges. For example, a graph that is consists of 4 vertices, we can write first vertex as a V1, second vertex as a V2, third vertex as a V3, and fourth one vertex as a V4. If we want to connect vertex V1 with a vertex V2, we use edge. This edge is labeled as a E1. The second vertex is connected with the third vertex. We connect these vertices using edge. This edge is labeled as a E2. The vertex V3 and vertex V4 is connected using edge E3. If a vertex V1 is connected with a vertex V4, and this edge is labeled as a E4. If vertex V1 is connected with a vertex V2, V3, this is labeled as a E5. If we want to connect vertex V2 with a vertex V4, we can label this edge as a 6, E6. So in this graph there are total number of 4 vertices, and we want to connect these vertices using edges. The total number of edges in this case is 6 edges. To connect all the vertices with every vertex in this graph, there are total number of 6 edges. We will see what is the relationship between vertices and edge. For now, we are just considering that a graph is composed of different vertices and edges. All vertices are connected with each other using edges. In a graph, edges can be directed or undirected. If an edge is a directed edge, then in a graph, if there is a vertex Vi and the other vertex is a Vj, there will be a path from vertex Vi to vertex Vj. We can move from vertex Vi to vertex Vj, but there is no path from vertex Vj to vertex Vi. Similarly, if this is a vertex Vi and the second one is a vertex Vj, and there is a directed edge from vertex Vj to vertex Vi, we can only move from vertex Vj to vertex Vi. There is no path from vertex Vi to vertex Vj. This is the case where the edges are the directed. The other case is undirected edge. In this case, if this is a vertex Vi and the second vertex Vj, there is an edge between vertex Vi and Vj. This edge is a undirected edge. In this case, we can move from vertex Vi to vertex Vj and from vertex Vj to vertex Vi. So the directed edge, this has a path that is a unidirectional, and in case of undirected edge, the path is a bidirectional. So these are the two types of edges we are going to use in a graph. First one is a directed. In the case of directed, we represent this directed graph as a line and with a arrow symbol. In the other case is a undirected edge. In this case, we represent this edge as a simple line. So we can move from vertex Vi to vertex Vj and from vertex Vj back to vertex Vi. Now if there are 4 vertices, there is a vertex V1 and we call this vertex as a city 1. This is a city. For example, this is a Islamabad, this is a second city, and this is a Rawalpindi. We label as a V2 or a city 2. The third one, for example, we label this city as a Jhelum, and this is a V3 or a city 3. The fourth one, we can label this city as a, for example, this is a V4, or we say this is a city Attack. So we label this city as a city 4. There are the roads that are connecting different cities. For example, city 1 is connected with a city 2 with a road, so we can represent this as a H. The city 2 is connected with a city 3, we represent this as H. There is a road between a city 3 and a city 4, and the city 4 is connected with a city 1. Similarly, there is a direct road from city 1 to city 3, and also there is a direct road from city 2 to city 4. So we represent the relationship of different cities in the form of a graph. Cities are represented using vertex, and the edges represent the road. From the city 1, if we want to move to city 2, there is a length of the road. For example, the length of the road is a 25 kilometer. The city 1 is away from the city 2 25 kilometer. The distance between a city 2 and city 3 is, for example, 35 kilometer. Similarly, the distance between a city 3 and city 4 is a, for example, 42 kilometer. And the distance between city 4 and city 1 is, for example, 38 kilometer. City 1 is directly connected with the city 3, and the road length is, for example, 50 kilometer. The road length between a city 2 and city 4 is, for example, 55 kilometer. As in this case, the edges are labeled with a weight or the cost. Cost is actually the distance. So the distance between a city 1 and a city 2 is a 25 kilometer. So this is called a cost or a weight of the edge. In this case, we have represented different cities, and the roads are represented using edges, and there is a cost associated with each edge. For example, the cost of the edge between a vertex V1 and vertex V2 is a 25. The cost between a vertex V2 and vertex 3 in the form of distance is a 35 kilometer. So this is weighted graph, and in this graph we have used undirected edges, so this will be called weighted undirected graph. Up till now we have studied what is a graph. A graph consists of different vertices and edges. The second one, what is the edges can be directional or undirectional. In the case of directional edge, there is only one path from vertex Vi to vertex Vj. In the case of undirected edge, we can move from vertex Vi to vertex Vj and from vertex Vj to vertex Vi. The second concept we have studied is the weight of the graph. In the case of the weighted graph, we have seen that each edge is labeled with a cost. For example, if there is a road between a city 3 and city 4, in this case the weight is a 42. We can represent real world objects in the form of vertices and the connection point in the form of edges. If in a graph every vertex is connected with each other vertex, for example, vertex V1 is connected with the vertex V2, V3 and V4. Similarly, vertex V2 is connected with all other vertices V1, V4 and V3. We call this graph as a complete graph. In a complete graph, each vertex is connected with every other vertex in a graph. So this graph is called complete graph. For example, vertex V1, this vertex is connected with the vertex V2, V3 and V4. Similarly, vertex V2 is connected with the vertex V1, V3 and V4. Vertex V3 is connected with vertex V1, V2 and vertex V4. And the last one, vertex V4, is connected with the vertex V1, vertex V2 and vertex V3. So what is the formal definition of a graph? So the formal definition of a graph is a graph consists of different vertices and edges. In a graph there are finite number of vertices and finite number of edges. We have already seen that if in a graph there are 4 vertices, we can connect all the vertices using edges. For example, this is a graph and first one is a vertex v1, second one is a vertex v2, third is a vertex v3 and fourth one is a vertex v4. Every vertex is connected with each other using edges. So the total number of edges in this case is 6 edges. In this case, every vertex is connected with each other using undirected edges. So this graph is called undirected graph. In a graph where we use directed edge, that graph will be called directed graph, or in a short, digraph. Digraph is short term that is used instead of a directed graph. Next, how we can calculate the total number of edges in a graph. To calculate total number of edges in a graph, we take one example. For example, in a graph, if there are 2 edges, 2 vertices, and we use 1 edges to connect these 2 vertices. For example, first one is a vertex v1 and second one is a vertex v2. We draw 1 edges to connect these 2 vertices. So if there are the first one is a vertex, second one is how many number of edges we are using to connect these vertices. For example, total number of vertices are 2, we are using 1 edge. In the case if there are 3 vertices, vertex v1, vertex v2 and vertex v3, we use 3 edges to connect these 3 vertices. This is a complete graph. For 4 vertices, the total number of edges are 6. So if there are total number of 4 vertices, so in a complete graph there will be 6 edges. So what is the relationship between vertices and edges? We can represent this relationship in a formula, and this formula is v into v minus 1 divided by 2. Now we see if a graph has 2 vertices, how many number of edges are evaluated in this case. If the value of v is equal to 2, we put value 2 here, 2 into 2 minus 1 divided by 2. So the total value comes out is 1. So in this case there are 2 edges, 2 vertices, and we are using 1 edge to connect these 2 vertices. The second case, if there are 3 vertices and 3 minus 1 divided by 2. In this case 3 multiplied by 2 divided by 2, total number of edges that are required to connect 3 vertices is 3. So in this case if there are 3 vertices, total number of edges in a complete graph will be 3. If there are 4 vertices, so 4 into 4 minus 1 divided by 2. In this case 4 multiplied by 3 divided by 2, and the total value comes out is a 6. So if there are total 4 vertices, total number of edges that will be used to connect these vertices are 6. This is the relationship between vertices and edges. If we know the total number of vertices, we can calculate total number of edges in a complete graph using the formula v into v minus 1 divided by 2. Or in a general, if in a graph there are n number of vertices, we can generalize this formula using n into n minus 1 divided by 2. So the general formula to calculate the number of edges is n into n minus 1 divided by 2. Here n is the total number of vertices. We have already seen what is a complete graph. In a complete graph, each vertex is connected with every other vertex in a graph. So the complete graph is represented as a kn. We write complete graph as a k, and there are n number of vertices. A graph can be represented in a two ways. First one is a adjacency matrix. The second one is a adjacency list. For example, if a graph has a two vertices, first vertex v1, the second vertex v2, and these two vertices are connected with each other, we can represent this as a adjacency matrix. This matrix will be 2 by 2 because there are total number of two vertices. We will write vertex 1, vertex 2, vertex 1, vertex 2, and here vertex 1 to vertex 2 there is a 0 distance, so we will write 0. From vertex v1 to vertex v2, these two vertices are connected using h, so we will write here 1. From vertex v2 we can move from vertex v2 to vertex v1, we will put here 1. From vertex v2 to vertex v2, because there is a no loop, we will write here as a 0. The distance, if there is a vertex vi, the distance of vertex vi to vertex vi will be 0. For example, from vertex v1 to vertex v2, vertex v1 we will write here as a 0. From vertex v2 to vertex v2, we will put entry as a 0. So here total number of vertices are 2, so this matrix is a 2 by 2. In the case if there are 3 vertices, vertex v1, vertex v2 and vertex v3, so vertex v1 is connected with the vertex v2, vertex v2 is connected with the vertex v3, vertex v3 is connected with the vertex v1. In this case, for our adjacency matrix, we will write v1, v2 and v3 in a row wise. So there is a column wise entry v1, v2 and v3. This is a adjacency matrix. So as we have already said that if there is a vertex vi, the distance vertex vi to vertex vi we will write put as a 0. Vertex v1 is connected with the vertex v2, we will put here as a 1. Vertex v1 is connected with the vertex v3, we will put here as a 1. Vertex v2 is connected with the vertex v1, we will write here as a 1. Vertex v2 to vertex v2 we will write here as a 0. Vertex v2 to vertex v3, because vertex v2 is connected with the vertex v3, we will put here as a 1. Vertex 3 is connected with the vertex v1, we will put here as a 1. Vertex v3 is connected with the vertex v2, because we can move from vertex v3 to vertex v2, we will put here as a 1. From vertex v3 to vertex v3, we will put here as a 0. So in this case, this is 3 by 3 adjacency matrix. We can represent a graph in the form of adjacency matrix. So we can represent a graph using vertices and edges, or we can represent a graph using adjacency matrix. If the graph is a weighted graph, for example, if the cost is written on a graph, if the graph is in the form vertex v1, there is a vertex v2 and vertex v3, and this graph has a cost associated with each edge. For example, the cost from vertex v1 to vertex v2 is, for example, 10. The cost to move from vertex v2 to vertex v3 is, for example, 8. And from v1 to v3, the cost is a 5. We can represent a weighted graph in a form of adjacency matrix as we will write vertex v1, vertex v2 and vertex v3 in a row wise, and in a column wise vertex v1, vertex v2 and vertex v3. Vertex v1 to vertex v1, the distance is a 0. From vertex v1 to vertex v2, the total cost is a 10, so we will write here 10. From vertex v1 to vertex v3, the cost is a 5, because we can move from vertex v3 to vertex v1 or from vertex v1 to vertex v3, so we'll put here as a 5. From vertex v2 to vertex v1, the cost is 10, we will put here as 10. From vertex v2 to vertex v2, the cost is 0. From vertex v2 to vertex v3, the cost is 8. From vertex v3 to vertex v1, the cost is 5. So we will put here as a 5. From vertex v3 to vertex v2 the cost is 8. We will put here 8. From vertex v3 to vertex v3 the cost is 0. We will put here 0. So this is a adjacency matrix. We can represent a graph using adjacency matrix. If we are given adjacency matrix, we can draw a graph. For example, if we are only given adjacency matrix, from here we can draw a graph. For example, first of all, we will write the total number of vertices. So the total number of vertices are 3. Vertex v1, vertex v2 and vertex v3. First entry is for a vertex v1 to vertex v1. We will not represent this as an edge. From vertex v1 to vertex v2 the cost is 10. We will put here an edge and its cost is a 10. From vertex v1 to vertex v3 the cost is 5. So we will represent this as an edge and this edge is a undirected. So in this case we will write here as a 5. The next value we will read from the vertex v2 to vertex v1. So already this has written and the cost is a 10. In the case of undirected graph, we can move from vertex v1 to vertex v2 and from vertex v2 to vertex v1. So we will replace this as a single line and we will put the total cost on this line. So the total cost in this case is a 10. In the next case we will read from vertex v2 to vertex v2 the cost is 0. From vertex v2 to vertex v3 the cost is 8. From vertex v2 if we move from vertex v3 the total cost is a 8. If we move from vertex v3 to vertex v1 the cost is 5. So in this case the cost is 5. As we know, we can move from vertex v1 to vertex v3 and from vertex v3 to vertex v1 we can replace this with a single line and we put here the value 5. So in this case we have replaced this with the undirected line and the total cost is a 5. From this entry we have seen that from vertex v3 we can move to vertex v2. So from vertex v3 we can move to vertex v2 and the total cost is a 8. So in this case we can move from vertex v2 to vertex v3 and from vertex v3 to back to vertex v2 and the cost is the same. So in this case we can replace this with a single line and the cost is 8. In this case the cost is a value having 8. So if we are given a graph in the form of a vertex and edges or in the form of adjacency matrix, we can convert this graph from vertex and edges to adjacency matrix or from adjacency matrix to in the form of graphical depiction. Adjacency matrix is used when our graph is a dense graph. In a dense graph we say that almost all the nodes are connected with each other. So the relationship becomes, first one is a complete graph. In a complete graph all nodes are connected with each other. For example, we have seen if there are total 4 vertices and the total edges are 6. In the case of dense graph, not all the vertices are connected with each other, but mostly vertices are connected with each other. For example, if we draw the vertices v1, v2, v3 and v4, so we have seen that there are total number of 5 edges. So the edges in a dense graph will be less than in a complete graph. So we can write this relationship as dense graph is total number of edges in a dense graph will be less than or equal to complete graph edges. This is the relationship between a complete graph and a dense graph. To represent dense graph and a complete graph, we use adjacency matrix. There is another type of graph that is called a sparse graph. To represent a sparse graph, we use adjacency list. So what is a adjacency graph and adjacency matrix or a adjacency list? In a adjacency list, we use a linked list. For example, if in this case we have 5 nodes and these nodes are connected with each other, we can represent this as a adjacency list. If this graph is a dense or a complete graph, we represent this as a adjacency matrix. So this is the relationship between adjacency matrix and adjacency list. We use adjacency matrix to represent a complete graph or a dense graph. Adjacency list is used to represent a sparse graph. We have already studied what is a weighted graph. Weighted graph has cost associated with each edge. So what is a dense graph? In a dense graph, total number of edges is close to maximal number of edges. So maximal number of edges are in the complete graph. The opposite of this graph is a sparse graph. The sparse graph has a few number of edges. To represent this graph, we use adjacency list. To represent a dense graph, we use adjacency matrix. Now we will study two concepts. First one is a path and second concept is a cycle. What is the difference between a path and a cycle? In a path, we start from any node. For example, this node is a U node and we want to reach at the node that is a V node. If there is a path from node U to V, we represent this as a path. For example, if the node V is linked with the node U, we say that there is a path from a node U to node V. If there is a no path, we will say that there is a no path between a vertex U and vertex V. In the case of a undirected graph, there will be a path if all the nodes are connected with each other. In the case of directed graph, there may or may not be a path between a vertex V and U. For example, we take a graph and the graph is written in the here on the screen. As you can see, if I want to move from a vertex 1 to vertex V4, there is a path from vertex V1 to vertex V4. If I want to move from vertex V2 to vertex V3, there is a no path from vertex V2 to vertex V3. For example, if I move from vertex V2 to vertex V4 and after reaching vertex V4, there is no path to vertex V3. So in this case, there is no path between vertex V2 and vertex V3. A simple path of a positive length that start and end at the same vertex, this is called a cycle. We have written what is a path. So the definition of path is if there is a vertex U and the other one is a vertex V, and if we want to move from vertex V to vertex U to vertex V, if we can complete a path from vertex U to vertex V, we say there is a path that is connecting vertex V to vertex U. If this path does not exist, we will say that there is no path from vertex U to vertex V. In the case of cycle, we start and end at the same node. So the difference between a path and cycle is, for a path we start from a vertex U and we end up at the another node that is called a V. In the case of cycle, the vertex u and v will be same. For example, if we draw different vertices, if this is a vertex v1, vertex v2, and there is a vertex v3, vertex v4, and we start from here, and this is a directed graph. Now we see, and we want to move from vertex v1 to all the nodes, and we want to come back at the vertex v1. So from vertex v1 we can move to vertex v2, from a vertex v2 we can move to vertex v4, from a vertex v4 we can move to vertex v3, and back up to vertex v2 and vertex v4, and again to vertex v1. So there is a cycle in this path. If the graph is undirected graph and each vertex is connected with every other vertex, there will be path. But in the case of directed graph, we have to analyze if there is a path exists between a vertex u and vertex v. After finding a path, if we reach at the start point, we say that this graph has a cycle. The last one is a acyclic graph. A graph that has no cycle is called a acyclic graph. Most of the case, the directed graph will have no cycle. So in the case of directed graph, there may or may not be a cycle. In the case of a undirected graph, if all nodes are connected with each other, there will be a cycle. In the case of directed graph, if there is a no cycle, we say this graph as a directed acyclic graph. As a graph that has a no cycle is called a directed acyclic graph. So these are the properties of a graph. In this lecture, first of all, we have seen what is a graph. A graph consists of different vertices and edges. Then we have seen what are the edges. There are two types of edges. First one is a directed edge, second one is a undirected edge. Then we have seen that what is a weighted graph. In a weighted graph, each edge is represented with a cost or a weight. Then we move how we can represent a graph. We can represent a graph using a adjacency matrix or adjacency list. Then we have seen what is a dense graph and a sparse graph. At the end, we have seen the difference between a path and a cycle. In a path, there is a starting node and there is a ending node. But in the case of a cycle, starting and ending node are the same node.